Your campfire is broken, not in the way a tool breaks when it stops working, in the way a tool breaks when it was never correctly designed for the job in the first place. Your campfire has been failing you by a specific, measurable, physical margin every single time you have ever lit one. And that margin is not small. More than half the energy in every log you burn leaves your fire as smoke before it ever becomes heat. That smoke rising into the sky above your campsite is not a byproduct of combustion. It is uncombusted fuel. It is warmth you gathered wood for, warmth you spent time building a fire for, warmth your body needed, drifting away into the dark because the design of an open fire is fundamentally incapable of capturing it. Welcome to Survival Secrets. If this channel is not already part of your life, this is the moment to join us. What we cover here is not the conventional outdoor industry narrative. It is the physics, the real mechanics of why things work or fail in a survival context, and what that physics tells you about where to spend $2 and where to stop spending $300. Today we are going to dismantle the campfire as a piece of thermal technology. We are going to explain exactly why it fails, using combustion science that has been established in peer-reviewed research since the 1980s. And then we are going to build two replacements, one that costs $2 and one that costs nothing at all, that between them solve every physical failure the open campfire cannot overcome. By the end of this video, you will never look at a wisp of campfire smoke the same way again. Because you will know exactly what it is. It is heat. It is your heat. And it is leaving. To understand what is going wrong with your campfire, you need to understand what wood actually is as a fuel source. Because the mental model most people carry, wood burns, fire produces heat, straightforward, is missing the most important part of the equation. Wood is not a single fuel. It is a layered energy storage system that releases its contents in a specific sequence when heated, and each layer of that sequence has completely different requirements for successful combustion. The first layer is the solid carbon structure of the wood itself. This is the charcoal layer, the glowing red ember bed at the base of a mature fire. It burns hot, it burns clean, and it is relatively straightforward to ignite and sustain. When people picture wood burning efficiently, this is the layer they are imagining. But the solid carbon layer contains only about 40% of the total thermal energy stored in the wood. The remaining 60% is stored in volatile gases. When heat is applied to wood, a chemical process called pyrolysis breaks down the cellulose and lignin in the wood structure into a complex mixture of combustible gases, methane, methanol, hydrogen, dozens of other compounds. These gases are released before the solid carbon even begins to burn. They are the smoke you see rising from a fire before it is fully established. They are the yellow and orange flames dancing above the ember bed of a mature fire. And here is the critical fact that changes everything about how you evaluate your campfire as a thermal system. Those volatile gases require sustained temperatures above 850 degrees Celsius to achieve complete combustion, not to ignite, not to start burning, to burn completely, releasing their full 60% share of the wood's stored energy. Your open campfire sustains temperatures between 300 and 400 degrees Celsius at the flame tips. The center of the fire may spike higher briefly and locally, but the edges, the upper flame zone, and the smoke plume all remain well below the threshold for complete combustion of volatile gases. The result is predictable and measurable. Those gases partially combust, producing heat and light, but a significant fraction of them escape the fire zone before reaching combustion temperature. They rise, they become smoke. They carry their 60% share of the wood's thermal energy up into the atmosphere and away from you. Every wisp of smoke rising from your campfire is a visible, real-time measurement of combustion inefficiency. It is not a sign that the wood is wet or the fire needs more oxygen in the simple sense. It is evidence that the design of the fire is incapable of reaching and sustaining the temperatures necessary to burn what the wood is releasing. The Aprovecho Research Center in Oregon, which has been conducting laboratory combustion research since the 1980s, has measured the thermal efficiency of open campfires consistently at between 10 and 15%. That means for every unit of energy stored in the wood you burn, you are capturing between 10 and 15 units of actual usable heat. The remaining 85 to 90% is lost to incomplete combustion, radiation in directions away from your body, and convective losses to the surrounding air. 10% efficiency. That is what you have been building every time you stacked logs and struck a match. The question is not whether you can do better. The question is how much better, using what, and at what cost. Before we get to the solutions, I want to ask you something directly, and I genuinely want your answer in the comments below. What is the largest campfire you have ever built? Not the most efficient one, the largest one. The one where you kept adding logs because it felt like the size was the point. Tell me where you were and what you were trying to accomplish. Because the instinct to build bigger fires in response to cold and darkness is one of the most universal human behaviors there is, and it is also one of the most thermally counterproductive decisions you can make in a survival context. I want to know how many people here have been there. There are two solutions to the campfire problem, and they come from completely different directions in history. One was engineered by indigenous nations on the North American plains centuries before European contact. The other was developed by a mechanical engineer with a doctorate from Oregon State University, who spent 4 decades in a laboratory before giving his findings away for free. Both solutions are based on the same core physics. Both dramatically outperform any open campfire. And between them, they cost somewhere between nothing and $2 to build. We're going to start underground. The Dakota fire hole was not invented. It was engineered. There is a meaningful difference between those two words, and the distinction matters here. The Lakota, Dakota, and Nakota nations developed this fire design under conditions that demanded genuine performance. They needed fires that produced minimal visible smoke, because smoke was a navigation beacon that communicated position to enemies across open prairie distances. They needed fires that resisted wind, because the Great Plains is one of the most consistently windy environments in North America, and an open fire on the plains is a fire being constantly disrupted and scattered. They needed fires that were thermally concentrated enough to cook efficiently, because fuel on the open prairie is not the abundant resource it is in forested environments. The solution they engineered addresses all three requirements simultaneously, through a design so physically elegant that military forces worldwide still use it today as a field cooking technique. You dig 2 holes approximately 12 inches apart. The primary chamber is roughly 12 inches in diameter and 12 inches deep. The secondary hole is smaller, approximately 6 inches in diameter and the same depth. At the bottom, you connect the 2 chambers with a horizontal tunnel. What you have built is an underground draft system. When you light a fire in the primary chamber, heat rises out of the opening. That rising hot air creates a pressure differential inside the chamber. The pressure differential draws air through the connecting tunnel from the secondary intake hole, which is exposed to the surface. Fresh oxygen enters the system continuously from below, at the base of the fire, precisely where combustion is most active and most in need of oxygen supply. This is not a metaphor for good airflow. This is Bernoulli's principle, operating in a specifically engineered geometry. Hot air rises and creates a low-pressure zone. Low pressure draws in high-pressure air from outside. The intake hole and connecting tunnel create a controlled pathway for that air movement that feeds the fire at its base rather than buffeting it from the sides. The consequences of this design are significant and measurable. Because oxygen enters from below, combustion occurs in a contained vertical column rather than scattered horizontally across a surface. The volatile gases released by the burning wood are forced to travel upward through the hottest part of the fire rather than escaping sideways. Temperature in the combustion zone climbs above what a surface fire of the same fuel volume can achieve. Smoke production drops dramatically because more of the volatile gas fraction is reaching combustion temperature before it can escape. The fire sits entirely below ground level. From any distance greater than a few meters, it is effectively invisible. The smoke signature, already reduced by improved combustion efficiency, disperses at ground level rather than rising as a visible column. In tactical contexts, this is why military field manuals include it as a standard technique. In survival contexts, this matters for entirely different reasons. Wind, which is the enemy of every open surface fire, becomes an asset. When wind blows across the intake hole, it increases the pressure differential and forces more oxygen into the system. An open campfire in wind loses coherence, scatters embers, and drops efficiency. A Dakota fire hole in wind burns hotter and more completely. You can cook over it by placing a pot directly over the primary chamber. The concentrated upward heat flow from a contained combustion zone is more efficient for cooking than the dispersed radiation of an open fire. Research data shows that water can be brought to boil approximately twice as fast over a properly constructed Dakota fire hole compared to an open campfire using half the fuel volume. The indigenous engineers who developed this design understood combustion physics in practical terms long before anyone had equations to describe it. They built the physics into the geometry of the hole itself. That is engineering, not accident. Now we go above ground. And this is where a mechanical engineer named Larry Winiarski spent 40 years arriving at the same physics from a completely different direction. Winiarski had a doctorate from Oregon State University and began working at the Aprovecho Research Center in Oregon in 1980. His stated goal was straightforward: build the most efficient wood-burning device possible using materials that anyone could find or afford anywhere on Earth. No proprietary components, no specialized manufacturing. No patents. Materials available in any village on any continent. After 4 decades of laboratory testing, iterative refinement, and real-world deployment across developing nations, Winiarski established 10 design principles that define what he called the rocket stove. He never patented it, he never charged for it. He spent the remainder of his career teaching people in developing countries how to build it from whatever local materials were available. He died in 2021 at the age of 81, having given away one of the most thermally efficient small combustion designs ever tested in a laboratory. Over 10 million rocket stoves have been built worldwide using his open-source principles. The outdoor industry sells $300 camp stoves with proprietary fuel canisters, titanium construction, and brand logos. Every single one of them operates on combustion principles that Winiarski documented and gave away for free in 1980. The physics is identical. The markup is $300 for the logo. The core principle of the rocket stove is the insulated vertical combustion chamber, which Winiarski called the heat riser. When you force burning gases through an insulated vertical column, 3 things happen simultaneously that are physically impossible in an open fire. First, the insulation prevents heat from escaping through the walls of the combustion chamber. In an open fire, thermal energy radiates outward in every direction from the flame zone. You capture only the fraction that happens to be pointing at your body at any given moment, which is a small fraction of total output. In an insulated column, that radiated heat cannot escape through the walls. It bounces back into the combustion zone, raising internal temperature progressively higher with each reflection. Second, the vertical column creates a self-reinforcing natural draft through the same Bernoulli principle operating in the Dakota fire hole. Hot air rises out the top of the column. Rising hot air creates a low-pressure zone. Low pressure draws fresh oxygen in through the fuel opening at the base. The hotter the column gets, the stronger the draft becomes. The stronger the draft, the more oxygen enters. More oxygen accelerates combustion. Higher combustion temperature heats the column faster. The cycle reinforces itself continuously from ignition forward. Third, the combination of insulation and directed draft creates an inescapable combustion pathway for volatile gases. There is no exit route from the column except upward through the hottest zone of the fire. Volatile gases released by the burning wood cannot drift sideways or escape through cooler regions of the flame. They either combust completely in the high-temperature column or they do not leave. The smoke itself catches fire. Aprovecho's peer-reviewed testing data shows rocket stoves achieving thermal efficiencies between 35 and 56% under optimized conditions. Compare that to the 10 to 15% of an open campfire. A rocket stove extracts 3 to 4 times more usable heat from identical fuel volume. In practical terms, one small handful of thumb-diameter sticks burned in a rocket stove produces the same cooking heat as an armload of logs burned in an open campfire. The sticks burn for 30 to 45 minutes of sustained cooking heat. The armload of logs in an open fire lasts 10 minutes before requiring replenishment. Now we build it. Because everything above is physics, and none of it matters until you can translate it into something that produces heat at your campsite tonight. The material is standard clay brick, not fire brick, though fire brick performs better if you can source it cheaply. Standard clay brick from any hardware store, any demolition pile, any construction site. 16 bricks. Total cost between $2 and $5 if you purchase them new. Free if you find them. which is easier than it sounds because construction waste and demolition debris generate enormous quantities of discarded brick in any populated area. Stack 4 bricks in a U-shape for the base. Leave the front open. This is your fuel shelf and your primary air intake. Build the side walls upward by stacking bricks on each side, 4 courses high. The front opening should be approximately 4 inches wide and 4 inches tall at the base. The vertical column above is your heat riser. That is the complete construction. 16 bricks, no mortar, no tools, no hardware. The entire build takes less than 5 minutes once you understand the geometry. Feed dry sticks of approximately thumb diameter into the front opening horizontally. Push them in only a few inches at a time. The tip burns inside the column. The rest of the stick remains cool enough to hold with bare hands. You control the burn rate by how far you advance the stick into the chamber. Push further in for more heat. Pull back slightly to reduce it. That is your throttle. That is precision heat management from 16 bricks. The inner walls of the brick column absorb heat from the fire and radiate it back into the combustion zone, approximating the insulation effect of purpose-built rocket stove materials. The natural draft system operates identically to the theoretical model. The volatile gas combustion efficiency improvement over an open fire is immediate and visible. A properly fed brick rocket stove produces almost no visible smoke after the initial startup phase. When you cannot build a rocket stove, when you need an open fire for warmth rather than cooking, or when the ground or surface conditions prevent construction, add a reflector wall. Stack flat rocks or green logs in a knee-height wall approximately 2 feet behind your fire. The wall serves 2 simultaneous functions. It blocks wind from disrupting the combustion zone and scattering heat, and the rock or log surface absorbs thermal radiation from the fire and re-radiates it back toward you. Position yourself between the fire and the reflector. You are now inside a heat pocket. The fire radiates heat toward you from the front. The wall returns absorbed heat toward you from behind. Energy that would otherwise radiate into the trees behind your fire is redirected back into your position. The temperature difference between the reflector side and the open side of the same fire is measurable and meaningful on a cold night. Use both simultaneously when conditions allow. The rocket stove for cooking, a smaller open fire with a reflector wall for sustained warmth while you sit. You are running 2 thermally optimized systems from the same fuel source, extracting maximum heat output from minimum wood volume. There is a larger point here that is worth making directly before we close. A $300 camp stove runs on proprietary fuel canisters that cost between $8 and $12 each. When the canister empties, you have an expensive piece of titanium engineering with no way to power it. You are carrying fuel dependency as a piece of gear. In any situation where resupply is not available, which is the definition of a genuine survival situation, that dependency is a liability. A rocket stove runs on whatever is dry and burnable within reach of where you are standing. Dead twigs, pine cones, bark strips, dry leaves compressed into a dense feed. Any combustible material of roughly thumb diameter or smaller becomes high-efficiency fuel the moment it enters an insulated column. The supply chain is the ground beneath your feet across any forested or vegetated terrain on Earth. A Dakota fire hole runs on the same supply chain and requires nothing but a digging implement and 15 minutes of work. Between them, these 2 designs give you cooking heat and warmth from materials that cost nothing, built from skills that require no tools, no supply chain, and no dependency on any manufacturer's product cycle. Larry Winiarski understood this. He spent 40 years making it as simple and as accessible as possible, and then he gave it away. The indigenous engineers who developed the Dakota fire hole understood it before anyone had equations to describe it. The combustion physics does not care about the brand name stamped on the equipment. It responds to geometry, insulation, and airflow. And those things can be built from bricks and dirt. Every campfire you have ever built has been throwing away more than half its fuel as smoke. Now you know exactly how to burn the smoke itself. Subscribe to Survival Secrets. New video every week. See you in the next one.